G'day guys, I just did a video and I swiped the screen to get into the editing mode, and I completely wiped the video by mistake, because it was going to be a video about Hall effect sensors and how we use them to, or what I've done anyway, how to detect the magnetic field from coils. Try not to pick up the flyback, and trying to optimize the magnetic componentry, basically just the structure of the coil and how the geometry to get really good reach and sensitivity on the device. But anyway, I'm back to the drawing board, so I'm going to have to do it again. I'll do it again. Damn. That was a waste. But anyway, I'll tell you what I've got here. Down there, so you can hardly even see what I'm pointing at, on the angle. This is my little amplifier setup, which I've done. It's got a offset, fine tune with that pot there, 100K. It's on the it's on the inverting input of the op amp, just to supply voltage, because the Hall effect transducer, which should be one sitting here somewhere. Yes, there is. This is a Hall effect device. They're very tiny, as you can see. I'll put on the blue. That's what it is. Looks like a little transistor, but it's got 5 volts ground and output, and that's all it is. Anyway, I've got one here, and I made up a cable, and I've stuck a bit of ferrite rod with hot melt glue on it, and that acts as a magnetic field line concentrator. You don't have to, but I have, just for fun, because I want to do some far field measurements with the coil. This is very bodgy, because it should be in a metal box. It should all be nice. What's happening is, because I've got the oscilloscope lead connected the way it is with a loop on it, it's going to pick up electric fields and display it on the oscilloscope. But what I'll do, what I've got here, I've got Mr. Commander here, and I'll put this thing back on the oscilloscope just to give you a quick run on this again. Oh, dear me. So basically what I'll do, I'll turn the detector on. Oh, I've got to plug it in. Would help. Okay, it's on. Now, if I get this here, and hang on a sec, I've got to put my power supply on too. I've got a battery regulated supply, which delivers plus or minus 5 volts. Now I'm going to take that off. Yep, and get that one off. Should put a switch on this. Okay, now I'll just got to readjust the pot and get that halfway. At the moment, I've got the coil resting on my lap with the detector on, so maybe something's getting warm down there. I don't know. Anyway, if you have a look at, I'll see if I can spin this around. I've got the coil here, and that's basically sensing the coil, and can't do everything all at once, can I? But you can see the waveform there on the oscilloscope. What I'm interested in is the bits going downwards. That's the magnetic, and you see those lines on top? That's the flyback. But because all this circuitry here is open and, you know, all iggly-piggly all over the place, it's picking up the electric field. If I actually point this at the circuitry, the flyback will really go completely nuts. If I put the coil halfway in like that, I can nullify it. And this is something to do with it also coupling in magnetically. For some reason it does this. It's really weird. Maybe I shouldn't point that out. Someone's going to go and patent something to do with it. But yeah, if I lift this up, you can see the flyback there go up, up, and if I go down, the flyback goes the other way. But if I go on the magnetics, right? You can see here that I go up. You probably can't see, but I'm going up and down with the coil the same way I did on the circuitry, and it doesn't change. Nothing changes in the magnetics of this, but the E field does. So on the coil, so I can flip things that way, and here it makes no damn difference. It's a bit horrible and a bit wiggly at the moment because, like I say, it's. I'll try and get it. Yeah, it's a bit. It is a bit difficult. I should have put like I say, I should take the whole day and mill out and drill and mount and make a really nice box. But that's how you can pick up the coil. You can make a far field magnetic structure, so you can make coils of the same size, same diameter, same height. Or if you've got some sort of wooden structure over it, you put your Hall effect sensors on. You can multiplex a whole heap of them together if you want to go and use an ADC or something like that. Or if you want, just shove it. You've got 4-channel oscilloscope, stick 4 of them into each channel. Or then again, you can adjust the offsets, the offset voltages on them. You know, maybe not directly 2.5 volts output, maybe 2.6, 2.7, 2.8. You're going to lose a little bit in overall dynamic range because you're squashing the voltage up, but you could have lots of them there and you can have a look at what's going on. But this is quick and easy and simple. Now, the way it works, I'll turn the detector off. So we'll drop that to the floor. And what I'll do, I've got to have the oscilloscope in there at the same time, otherwise you can't see what's going on. Say, for instance, look at a stack of magnets. Gee, this is deja vu. I did this about 15 minutes ago. But say I hold it that way and I go near in front of that ferrite, good 18 inches away or so, okay? And I'll go towards it. I was just going up and down then. So if I go towards it, okay, you see it going downwards, and I flip the magnet round and we go upwards. So it responds to north and south poles. They're interesting thing, Hall effect devices. Have a read up on them and see how they work. They flick electrons to one side of a plate and then the other, depending on magnetic interaction. Also, these things too, some of them you can put very fast waveforms through these, and they all give you a fairly accurate representation of up and down to what the waveform is. I think a lot of the cheap ones clap out at about 50 kilohertz. Some of them you can get a good to 100 kilohertz, and there's some very nice exotic ones out there which are pretty expensive, and they're good to a megahertz or so. So you can depends what you want to use, but basically the coil's doing that, and that's what that's going to do, right? And if you stuck it on a 7000 with this, it would do this really quickly as the transmit field changes pole, because that's how that thing works. Do I have to say in my opinion? But yeah, like so. Really fast though. I can't twiddle it that fast with my fingers. But yeah, that's how it works. Very, very simple sort of a thing. Like I say, they work by themselves. You don't need this ferrite stuck there. The other thing too, with the orientation of these, I'll try and, like say if I got it like so, and then I pointed at the bench. See, it's picking up some magnetics. It could even be the transformer or in that you'd hope not, but it might be picking up the transformer in the oscilloscope or the transformer in a power supply or soldering iron or something. And if I turn it around the other way, like that, yeah, it goes off in the other direction. So obviously it's picking up a field of something. And the other thing too, if we poke it down, it goes up, and that's why I have an offset adjustment potentiometer, and if I go that way it goes down. So you can make a big long one of these, and you can take it out in the field, run a lot of amplification. You can track down detector operators, because it'll tell you if it's coming from that way or that way. Ah, dear me, quite funny. But like we used to do when we used to hunt people down with radio, when they had illegal radio transmitters, we used to get it in with our antennas. We used to get it end on with beam antennas and make nulls, because we knew where the null points are, and that was exactly where it was pointing. So, like that, it's a bit of an arc. It's not very accurate, but on a null it is. So that is that. Now, I'm going to unplug this because I haven't got the audio on. I didn't know if it was on or off. Hopefully it was off. And it's off now. So basically all I've got there is stick your fingers in there. All I've got in there is and down we go. That might help. There's an op amp. I just put it on a little board. There's a converter board from dip to SOIC, and use that the dip pins as so I could push it into this proto board, and just all you gotta do is put the pot between your voltage rails and onto the inverting input of the op amp, which on most op amps of that type is pin 2, and Hall effect output goes on to pin 3. Positive voltage goes on pin 7, negative voltage on pin 4, and output voltage on pin 6, which goes basically, I've got a capacitor across it just to get rid of some of the noise, or that capacitor might actually be on the output of the Hall effect device. I should have one there as well. I haven't, bad luck. Feedback resistor there, I think I've got 100k in there or something like that. So you look at the ratio of whatever the resistance to ground is on this to the non-inverting input, and then divide that into the 100k. It'll probably give you roughly how much gain it's got. So, but we're not worried about that. We're just using it as a set point setup. So you adjust that, it's going to adjust the gain. So it's not a set value. You probably do it different ways. But that's a quick and easy way to do it. It's just a basic op amp, non-inverting amplifier. That's all it is. You can get the output directly out of the Hall effect sensor, but I think it's a lot better if you buffer it. It's you're going to get a lot more out of it. You get more range. I've tested this so far with a coil. I can get 1.5 meters out of it just on a 11-inch coil, and that was with this sitting at 100 millivolts per division. I can get this down to 2 millivolts per division, so it'll go out a lot further than that. I can probably get 3 meters or 10 feet out of it, and it'll still pick up the magnetics. But like I say, it needs to be in a metal box. It needs to be screened properly. You don't want temperature fluctuations on these. That should more likely go in a little bit of PVC tubing, and so there's no circulating air currents getting around it. Bit protected so you don't get fast air movements. If you do, I've got it sealed there at the moment. It's sealed up in hot melt glue, and I just stuck everything together like that. It shouldn't move around very much, but as you can see there, because this is all open structure, that it's picking up a lot of noise off the equipment on the bench. Okay, we'll turn the power supply off. This is a lot quicker video than the last one anyway. The other one went for ages. I sort of condensed this down because I didn't do the punctuation of waffling in the middle of the video, going off on tangents. So yeah, that's it, turned off, and that's that. You can make these up yourself, very easy. The one thing which I think, and I suggest that you do, which I'll just pop this out really quickly because I know where it goes. Out of there, please. The cable, I've used two basically inert, as in you wave this over the detector coil and it doesn't sound off, because it's made out of very, very fine strands of tinned copper wire. And I say tinned on purpose, very fine on purpose. If they're thick copper strands, it will sound off, especially if they're over about 0.2 millimeters. Depends on the clocking rate and stuff too, and there's a heap of factor to take into account. But that there is more or less because the other end's going near the coil. You don't want big pieces of metal or plain copper stranding and stuff like that. It probably interfere with the coil. I haven't tried it. I suspect it will. Maybe it doesn't, because we're looking at the magnetic component, not the electric field. So, but then again, who knows what happens if you haven't done it? There's a lot of stuff, like I read stuff in textbooks and it says da 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 whatever, right? And a lot of cases, I will go and do it and prove it, because a lot of stuff, I'm always one for seeing is believing. Sometimes, things that have came about in, the late 1800s, probably a little bit more refined these days, and we can actually check it a little bit better than what it was, and everyone takes it for granted that that's the way it is. Like all those sharp pointy things we all had a couple of years ago were safe, weren't they? They're all safe, very, very safe. And now it's being looked at as not being so safe. So always good to recheck everything. Go back and look at the fundamentals. So that is that. All I got to do now is make myself up some sort of wooden structure, like something like that, put the Hall effect device there. I want it probably on some sort of sliding rail. Also, it's got to be made of plastic or not metal, and then you can move it this way or that way, or even if you want to move it that way and up and down, you can map the field of the coil. There's probably someone make a nice automated process to do that, or you use lots of Hall effect devices and take the data from all those. And just remember, you change the diameter, right? It's going to give a complete different reading on your sensors. You've got to compare particular size coil with a particular size coil. You can change the windings, do it whatever you want to see what happens, what's effective, what's not. Is that coil got half its wire strands have all come off, and it's not putting out much of energy, stuff like that. Because look, I've had coils and I've pulled them apart, and even when they were made, I'll tell you what it actually is. Because all the lids is a little bit off course, but so what? It's good to know that I've pulled coils apart before, and plugs and connectors, and the Litz wire, because each strand is insulated, it's got varnish on every little tiny strand. So it's 100 strands. They're all 100 separate, not connected strands, unless you solder them all together. Now they're all connected, and you do it at the other end, they're all connected. And basically what happens is sometimes people are a little bit quick, and they use solder pots to do it, and they go into the solder pot, and all around the outside solders up, and all the ones in the middle basically haven't taken. They're basically just sitting there under the blob of solder. And in a lot of cases too, when they do it, especially on the braid, they twist it, and because it's all twisted, they cut it. There's a whole heap of short strands and long strands, and when they do a tail to solder it, half the damn strands don't end up getting soldered. So, half the metal, half the conductivity of the braid is, it's not being utilized. So thus current can't flow as well as it should, and doesn't energize the coil properly. So that's why you may find differences between coils. It depends. If it's an old coil and it goes a bit, oh God, it's not doing much, it'll still work on the detector. Some cases it will, some cases it won't. You can break a lot of strands off. like when I was saying on these, with this system here, with the with the bung in here, the little rubber bung and the concave convex parts that squash down like crazy on it, and then this moves a little bit and it starts breaking all the braid strands, and the coils start, not working as well as they once did. That's why all these, if you ever look, even on this one here, that is not tight. That's that. I would never, as soon as I get any coils like that, bang, I just take that off. I just loosen it off. And a lot of cases I wiggle it around there and I just get something sharp and I pull that rubber bung out and throw it to wherever. If you really want to seal it up, fill it up with petroleum jelly or some sort of silicone grease or something like that, and then put it together. Don't rely on tightening it up with that bung in it, because it'll bung it up. Something like that. No, it's true. I've had to replace so many cables over the years, especially on old coils where they've been used a lot, and people, they use them to pinpoint. They're always bending it down and up and down and up, and it goes. This is tied hard onto the shaft, and it just goes and it pops all the bloody copper strands. So there has been quite a few of those over the years. That's why they all went to those flat bung type things, which, I did years and years ago. Dear me. So that's where we are. God, it's 8 o'clock. Okay. Well, so anyway, you can make little coils up to do this sort of stuff on your detectors and use it for measuring, but you get a lot of interaction because it's going to pick up flyback as well. And it's not just working on the magnetic component, it's also susceptible to electrical fields. You could also have noise issues. If this was all sealed up nicely, it would be nice and clean. It wouldn't have all that fur over the waveforms, and I'll be able to get down to probably maybe 2 to 5 millivolts of division and keep it there stably. Anyway, enough of that. So instead of being 40 minutes, this is 22. Catch us.